Chen. So the presentation we'll be doing is the journey of Presto towards cloud at Uber. Okay, how should I? Okay, so we'll go over the agenda first. So we'll be going over the overview of Presto at Uber, followed by the migration overview and what all queries are getting routed to cloud and how we are doing it, and the enabling security on cloud, and followed by some of the challenges which we faced during data migration and some of the learnings along with the future plan. Okay, so in general, Presto at Uber looks something like this, where we have 4 regions, and we have around 9,000 active users per day, and we have 51 clusters, which comprises of 17K nodes, and we run around 690K queries per day, which reads around 150 petabytes. So this is one step further where it is like a cloud footprint. So out of those 4 regions, 2 are in cloud, and we serve around 7,000 active users from cloud, and 23 clusters are in cloud, which serves around 8K nodes, and we run around 320K queries already, which is like more than around 50% of queries are currently running from cloud, which reads around 80 petabytes. Okay, let's talk about migration. So this is a view of Presto before cloud. This is just on-prem, where we had a primary and secondary, and all the queries come via QR, which is like a query runner platform. And it goes through validation and does load balancing. And depending on the type of query, it either goes to interactive or batch or some other clusters, depending on the use case. And we had all the queries go to the local HMS, and the data sits in data lake, and the data gets Hive synced from primary to secondary. So this was the overall picture on how the Presto was set up before cloud world. And once we moved to cloud, or once we started migrating to cloud, this is the overall picture where all the clients come to still goes to the QR in primary region mostly, unless in case of DR, and it goes through the load balancing, and the query ends up in mostly primary on-prem and primary cloud. But during this cloud migration, we had some issues like capacity and some limitations of egress in cloud on the primary region. So we started using some of the capacity from a DR cloud as well. So currently it is, at least in cloud, at least we are running active, where currently the primary traffic goes to primary on-prem, primary cloud, and DR cloud. Okay, so left side is something which we started with when we started the cloud migration, where we did the validations with the local HMS, and then the queries get routed to cloud. This was working fine till most of the cases where all the tables were primary in on-prem. So the validations were going through without any issues, and things were running fine. But when we started to move more and more tables to cloud, and when some of the tables were getting primary on cloud, this was no longer a viable solution. So we ended up moving the validation service to a place where it will query its own HMS. Like wherever the query is getting routed to, that the validation happens on that HMS, so that this issue can be avoided. This we did it very recently, probably a couple of months before. And yeah, and we also support 2 types of routing to cloud, explicit and implicit. I've just given a brief of what each of it is. So implicit routing means like within the load balancer, we decide where the query ends up with, whether it goes to cloud or on-prem, depending on the capacity, depending on the data availability, and bunch of other stuffs. Whereas the explicit routing is something where a user decides that this query has to go in this region, whether it is on-prem or cloud. Yeah, depending on their use case. So one easy use case is like data quality checks, where they want their queries to end up in one region, and we can't move it based on our use case, right? So yeah, those are majorly how we route queries to cloud. So this is internally how we validate the queries and whether the data is available in a particular region, right? So Prion is an Uber inbuilt validation service where the query which comes via Presto connector goes and checks this API, table access API, and that creates an AST tree, and it parses it and gets the bunch of tables which are getting used in that query. And it also collects the tables which are just accessed and the tables which are getting updated as well. So this will give us an information whether the table is a right query or not, and it also gives the table accessed. So currently we are only implicitly routing read traffic. No write traffic is implicitly routed to cloud, but explicitly we are allowing that. So this enables us to do that. Okay, so this is the timeline in which we did the migration. This is like the entire journey which we have taken till now. And like the journey started in majorly on February. We were doing some POCs before that, but the onboarding to cloud started in Feb this year. By March, we were running like 20% of low tier traffic. And by June, we were running like 35% of entire Presto traffic on cloud. And latest, we are running around 51, 52% of the total Presto traffic on cloud. Okay, query routing. So let's assume we have 3 regions with different data availability, like percentage of data available at different scale, and we also have different capacity, right? So this is where we are currently at, where we have multiple regions with different capacities and different data availability, and how we are like routing the queries to each region, right? So that is based on this. So we have different percentages here, which we fine tune depending on the capacity available in that region and the data available, right? So say suppose we have a query which comes in and it checks the first region and the data available is 50% in that, and the percentage we set is 20%. So there is like 10% chance that the query goes in region 1. And if not, then it checks for the second region and where the data available is again 50%. And this can be the same 50% as region 1, or it can be the complete opposite of it, right? So depending on that, and say suppose we have 40 to serve 40% of queries, we have that much of capacity in region 2, then we, depending on these two things, we will be routing around 16 to 20% of the query in region 2. And everything falls back to the last region, where you can consider this as like an on-prem region where you have 100% of data available. So all the queries which can't be served in first 2 regions falls back to the last one. Okay, so a little bit more details on it, right? Like, so we have for every query, it checks. We have another inbuilt service where it gives you details on whether a list of tables is healthy on a region, or it is just available but it is not healthy in compared to the primary region. So we get all those information for each of the regions where the where we have the capacity and where we can run. So first we check the list of healthy regions, and based on that capacity availability, we have the percentages set for each of the region as we saw before. And the queries, mostly we try to run those queries which are healthy, mostly we try to run the queries in the healthy region. And say suppose for a query there is no region which is healthy, then we try to run it at a region where the tables are available even though it is not healthy, right? So this can happen because we join with multiple tables and few tables are available or healthy in some, not healthy in other, right? So in those cases we fall back to all the available regions. But say suppose there are like more healthy queries than the percentage is what we set. So the extra queries which falls out of these ranges will be served with the last region. This is like a catch-all kind of region, but based on the analysis and based on the health, what we have seen, like we are seeing like more than 90 to 95% of the time, the health like remains the same. It doesn't go out of like unhealthy status or something. So we are in a good shape to manage this without any issues. Okay, so we majorly run queries in batch and interactive, and this is like some sample configs which we are using. And during the cloud migration, we also have got few requirements, and because of which we added few more attributes to like on how we can decide which queries ends up where, right? So routing percentage is one, and similar to that, we have other things where we can set some fingerprints, and depending on the fingerprints, we can say these fingerprints has to go in like primary cloud or DR cloud or something of that. And we can even mention like if these tables are available, then go only to this region, right? So those kind of use cases we have enabled so that like users don't get different results which they are not intended to. Okay, so Chen will continue on security.
Okay. Okay. So yeah, thanks, Vineeth, for the first part. So I'm going to talk about some other stuff that is not specifically related to Presto, but also about its ecosystem. So to me, I think there are only two major domains that sees differences when we migrate to cloud. One is security, the other is storage. And I'll talk about some of the things and how we kind of adopt those changes. So starting with security, just a quick overview of the authentication kind of overflow on-prem. So at Uber, we are using heavily depending on the Hadoop delegation token. And so it's in some way very similar to how you run a YAR application. So the query client are going to request a token from token service, which is basically going to call HFS to get a delegation token from name node and then send it back to the client. And then client submit the query along with a token to the routing layer, which then send to Presto. And then at the Presto coordinator, it will just call HFS name node to authenticate that delegation token. If it's authenticated, then it's considered authenticated by in the cluster, Presto cluster. And then the token is dropped, and then the Presto worker will just read data using impersonation to create a proxy user and read from HFS directly. That's kind of how it works on-prem. But in cloud, of course, it's going to be a different paradigm because cloud, simply put, cloud doesn't speak Hadoop tokens. It has its own OAuth2, the access token for GCS, for example. So, of course, one way is to just change everything to start adopting this new token, but that means changing a lot of the components in this diagram. Everyone needs to basically update it to speak a different token, call a different endpoint, and maybe making smarter decisions of which endpoint to call depending on whether it's on-prem or on cloud. So this will not be very efficient and will not scale up very well. So the solution that our cloud engineering team come up with, and we collaborated with them, is to have this new layer, like a cloud token broker. So it's basically, the idea is that we hide all this difference from the Presto layer. So everything to the left remains the same, exactly the same on-prem. So in the Presto world, it still thinks this is speaking a Hadoop delegation token. But in reality, this token is generated by this cloud token broker. And so the authentication flow is still the same up to the coordinator authentication. So, but instead of authenticating against HDFS, it's authenticating this new service. And then when later on, the Presto worker needs to read data, this is where this cloud token broker will need to do some translation of fetching the real cloud access token and giving it back to the user. Presto worker, so that the read can proceed. So the good thing about this is, on the one hand, everything stayed the same, so we barely need to make any change instead of maybe just a couple jar or a configuration update, and then it just works out smoothly. And also, on the other hand, it only requests a cloud access token when the read is actually happening, so that we kind of minimize the number of calls to the cloud storage. So yeah, this is currently in production and has been scaled pretty well for us. So yeah, that's kind of on the security side. The other adoption, I would say, is an even bigger challenge, is about the data migration challenges. So there are a lot of things we can talk about in this domain, but like there are only two things I want to call out today in interest of time. So the first one is what I call a query coverage. It's basically the fact, the reality that there will be a long period of time where certain tables are already migrated to cloud, but certain tables are not, right? Because they're only limited bandwidth of ingesting data to cloud. So we can only move data this fast. And also on the other hand, the cloud storage is provisioned like stage by stage. So at a given point in time, we only have this much storage capacity in cloud. So what that means is that there are a lot of restrictions. So we have to live with the fact that the table migration is going to take, say, even months to years to complete. So, and the problem for Presto is that if a query is kind of trying to read multiple tables, maybe doing a join or something, we need to make sure that all the tables are in cloud for this query to be able to run in cloud. We don't want to be in a situation where we migrate a lot of data, but none of the query can run because they're all trying to join tables from cloud and on-prem. The other side of the problem is what I call the consistency, which is basically that even for those tables already migrated to the cloud, the ingestion still continues the way that it's first ingested to on-prem and then it's being synced to cloud. So there'll be a sync delay between the data is present on-prem and until it's being present in cloud. So we need to deal with those kind of situations. So yeah, I'm going to talk about this too, like in more details. So for the query coverage, so basically you can think of this kind of the algorithm problem in some way. So you have a list of tables and you have a list of queries. And the queries each have a CPU time and also they need to join some tables. And for table, they have a size, right? So then this is basically about finding the right set of tables that gives you kind of the highest query CPU coverage. Right? So this is basically a set cover problem. It's a well-known NP hard problem. There's no really efficient solution. So what we did is also kind of approximate greedy heuristics. We built this procedure to basically find the top one most accessed table and see what are the common tables joined along with this table, and then kind of put that into as a tuple. And we list out kind of a list of tuples and maybe picking the top n and giving those tables to our migration team and say, okay, so in this iteration, we want to migrate these tables. And that we know for a fact that this will allow us to run this many queries with those CPUs. So we kind of do this iteration by iteration from over time. We just give them batches of tables, and then they will pick these tables in their own cadence to migrate the tables. And this process has been working well for us. I mean, it's not optimal again because it's it's a NP hard problem, but yeah, it's been working fine for us. So by that I mean this is basically like a kind of retrospective like look at this methodology, right? So we did a lot of analysis, and there's one result of it. So as you can see, some, I guess, maybe hard to read, but basically showing like the top 1,200 tables would be able to cover like 75% of queries. And also they probably together have like 100 petabytes of data to serve those queries. So this kind of giving a sense of like what metrics we look at in terms of the query coverage in this challenge. And then the other challenge is about data consistency, table consistency. So again, like I mentioned, the problem here is about the sync delay from on-prem to cloud, right? So in many cases, I would say in most cases, the delay is only a matter of a few hours. So it's not a big deal for most of the like batch traffic. But there are indeed cases where the users really want to have the updated data in their query. So what we did is like we have this, we introduced a new service we call table availability service. It's basically talks to HiveSync to collect all the information of which table is up to date to what point, right? So then when we make this decision of whether route a query to cloud or on-prem, it first queries this service and see, basically ask this question, are all these tables in this query up to date? Right? So only if the answer is yes, this query is considered like eligible to cloud. Otherwise, it's basically route back to on-prem. But there are a lot of knobs we can play here. For example, instead of returning a single yes or no, maybe we can return like cutoff time. So this table is only up to date until this point, right? Then we can make even more fine-grained decisions, like if the table is like, let's say, only 2 hours behind, then maybe it's still acceptable, or something like that. So yeah, this actually gives us a lot of power to determine like what queries to migrate and like what kind of SLA we want to meet. Yeah, so that's also in production as being serving like all the 50% of our cloud footprint for us. And then I want to talk about some learnings. So apparently there are a lot of learnings, but like I want to talk about some of the most interesting ones. So the first about storage egress cost. So I think there's a major like kind of mindset shift in terms of running on-prem versus running on cloud when it comes to storage. Right? So when you're operating on-prem, HDFS, for example, is kind of traffic irrelevant in terms of cost. What I mean is that when you provision a HDFS cost or try to calculate the storage cost, you basically pay the cost to set up the cluster and wire them up. Then you just pay the electricity bills, right? Reading 1 megabyte or reading 10 megabyte or 100 megabyte doesn't really change the equation of the cost. But in cloud, the every egress request is being charged. So that is really depending on your traffic. So, and the implication of that to Presto is that a lot of we need to rethink a lot of performance optimizations in terms of read. For example, one case we had is that the cloud client has a built-in prefetch feature, where basically, although maybe it's only requesting 100K bytes, we're actually reading 2 megabytes as a prefetch. The intention is to be optimization. So because if the next read is also in the same range, then it saves one request to cloud. But that can also have other downsides, because if you miss the prefetch read, then it kind of wasted the other prefetch bytes. And this turns out to have some major impact to the operation, because we have actually had this case where a lot of prefetch are just like wasted. We had to fine tune the prefetch read. For on-prem, this would not be a problem. I mean, because we have enough HFS bandwidth, so let it wasted, right? It doesn't hurt anyone. But in cloud, it becomes a major issue in terms of cost, right? Basically, we're paying a cost for nothing, and we got like a complaints and reports on that. So we have to fine tune those performance optimizations. So the point here is that there's another orthogonal dimension of optimization. On-prem, we just care about like performance improvement, right? But in cloud, there's this new dimension of read cost. So every feature needs to be put into this new calibration to see like, is it worth putting into production or not? As I put here, so the implication here is that the read reduction technologies are becoming even more important in cloud. I mean, generally they are good improvement, but in cloud they are even more critical. By what I mean is like features like push down in Presto that reduces some read, and also local disk caching, and also like reduces read from remote storage. And another aspect of dealing with cloud storage is what we call a data mesh. So the problem here is like this. So although the cloud buckets claim to have infinite like capacity, but the bandwidth is still limited. And on-prem, we used to have like maybe a dozen of HDFS clusters, but in cloud, to be on par with that in terms of bandwidth, we need hundreds of buckets. And then that brings this problem of which table should go into which buckets, right? So this may sound simple, but it's actually more difficult, more challenging than that. For example, if my team have a list of tables, and if you just blindly throw them into different buckets, then there is a chance that those top tables go into the same bucket, and then they're being capped by the bandwidth limit of that bucket. So we need to be very smart, like a big table go to their own buckets, and small tables can share buckets, things like that. So then we need to have like some intelligence to manage this whole complexity. And there's another dimension, which is the access control. Right, so on-prem is just HFS echoes, very easy. But on cloud, there's another layer which is cloud enforced access control. Like buckets have their own access controls. So the idea is that we want to map what do we have on-prem to what do we have on cloud, right? So if a team, say, has access to certain data, they better still have the access to those buckets. And on the other hand, if a team doesn't have access to certain data, they better still don't have access in cloud. So all this complexity is like basically comes into this idea of how do we manage the mapping from the on-prem data layout to their layout in cloud. So to manage all of this, we introduced this new service called Data Mesh. It actually has more functionality into this. It's a very it's oversimplified view of the service. It takes input from HMS and access control. And when we do a Hive sync, the Hive sync will talk to Data Mesh and to provision all the echoes accordingly. And also Data Mesh will tell Hive sync which table or which bucket should this table be migrated to. And this is actually becoming more important in our operation because this actually turns out to be the best place to add a lot of other functionalities, for example, quota management, data governance, and other things. So this will becoming, expected to becoming more and more important to be the central point of our cloud operation. It's kind of completing our cloud data governance story. Yeah, so those are the learnings I want to share. And last but not least, I want to talk about some future plans. Though what we're working on is Prestissimo and Velox on cloud. I believe you have heard a lot of this in this today. So we are already operating one Prestissimo cluster in cloud, replacing one Java cluster already. And it's serving some percentage of cloud traffic even just now. And we are doubling down on this. Well, continue investing this to make Velox have a larger footprint in cloud. And another thing is cache as a service. So like I mentioned, the read reduction technologies will be even more critical in cloud. So we are looking to have better caching service. We're already extensively using a local cache feature, but now we are thinking of can we do even better, right? Have a easier to scale up cache service in cloud. And also the last one is about hybrid storage and remote reads. So far, the story has been like the data is duplicated. It's on-prem and has duplicate copy in cloud. But of course, that's a duplicate data and can be costly. And so we are thinking of possibilities of doing a hybrid mode where for a table, for example, for one single table, some partitions are on-prem, but some are in cloud. But to be able to do that, we will need to have the remote read or hybrid storage feature. That is work in progress, and we have already have some success. Like I believe already have some tables in this mode. Yeah, we'll continue investing in those things as well. I think with that I think wraps the presentation. Now I think any questions? Yeah.